Welcome to this presentation on 3D dynamic image particle analysis by Microtrac. There's apparently a lot of growing interest in dynamic image analysis for particle characterization, and particularly in 3D image analysis. Our aim here is for you to take away a good understanding of dynamic image analysis in general, and especially to see how the 3D mode works and contributes to providing such more accurate size and shape information of the sample analyzed. We'll also touch on two interesting features, classifications, and filters, which can only be done with image analysis technology. Particle morphology characterization has a very long history. The only tool analysts had originally was a manual optical microscope, not even as modern as the one shown above. A small sample of particles was distributed as evenly as possible on a glass slide. The slide had square grid marks etched on it, and the sizes of the particles were estimated by comparing their length and width dimensions to the grid lines. Ratios of different sizes were calculated to gain some basic shape information, like dividing length by width to get aspect ratio. Many individual samples had to be measured to get a representative result, and one analysis could easily take all day or longer. Fortunately, today, with the advent of very high-speed digital cameras, high-speed strobe lights, rapid CPUs, and ever-increasing mass data storage, this old static image analysis method has been converted into automated instruments dynamically flowing hundreds of particles per second through a sensing zone where digital images of them get stored and upwards of 30 different sizes and shapes parameters calculated and reported in usually less than a minute. And if that critter on the right gets into the sample, he can be filtered out with the software. This is the set of parameters that Microtrac reports for its Partan dynamic image analysis product line. Rather than go into each in any detail, I'll describe in four general terms, the column headings, what they measure. First, of course, is size. We give you 15 different size measurements of each particle in various diameters, lengths, widths, thicknesses, and more. The last three columns are shapes of different natures and are generally expressed as ratios of size parameters. The form factors include a number of different parameters that indicate how closely the particle is to being a perfect sphere, or various aspect ratios or elongations of the particle. Surface roughness parameters are just that. We have three different parameters that can indicate the roughness factor of the particle surface. Other parameters report the overall transparency as light intensity coming through the particle, and the curvature of the particle as a gradient of the light intensity. And last, each image in each frame is given an ID number for bookkeeping purposes. A little history on Microtrac's Partan image analysis product line. 1985 marked the start of development of an online dynamic image analyzer for Norsk Hydro Research Center in Norway. The first online Partan was installed at Norsk Hydro Norway in 1987, which gives this product line 27 years experience in the field. Analytical was founded as a manufacturer and supplier of image analysis instruments in 2004. The 3D software was released in 2008, and Microtrac acquired Analytical technology in 2013, about 4 years after Microtrac and Analytical had established a marketing alliance. So Microtrac has 4 years experience selling this technology and is now developing and manufacturing it. Here's a schematic which shows the simplicity of dynamic image analysis as used in the Partan 3D analyzer. The dry sample placed in the funnel on the right moves on a vibratory feeder to the edge of the sensing zone, where it falls by gravity through the sensing zone and is collected in the sample box at the bottom. A light strobe on one side of the sensing zone lights the particles as the digital camera on the other side photographs the particles as they tumble through the sensing zone. A video file of the analysis is stored, and distributions and summary data for 30 morphological parameters for each particle are calculated and reported. This is an open instrument photo of the analyzer. The particles are seen tumbling through the sensing zone, while the strobe and camera record the video file of the analysis. This video file can later be recalled and rerun under different measurement conditions, or it can be overlaid on a graph of a series of historical data. The sample analysis technology could hardly be more simple or robust. And neither could the method of parameter measurement. An enlarged digital image is shown here, large enough to see the pixelation. Just knowing the size of the pixels, all the size and shape parameters can be easily calculated. And no a priori knowledge of the materials is needed, like refractive index, density, or viscosity, as they are in other size analysis technologies. Here is one of several results displays in the Partan 3D mode software. Notice in the graph and table windows, top left and top right, that not only are the length and width size dimensions displayed as they are in 2D analysis, but the distribution of thickness, the third major axis, is also reported. And they are in the size order that would be expected. Length, the black curve, is largest, width in green is second largest, and thickness in red is of course the smallest of the three major axis dimensions. The window in the lower left allows the user to select different parameters to report, and user selectable summary data are displayed in the lower right window. Here are some photos of both 3D image analyzers. The Partan 3D with a range of 15 microns to 30 millimeters in the upper left, and the Partan 3D Maxi 0.28 millimeters to 100 millimeters at the bottom. An autosampler accessory for the 3D is shown mounted in the upper right. This diagram shows the basic 3D measurement technique patented by Analytical. A particle tracking algorithm is used to take multiple photos of each particle tumbling randomly through the sensing zone. The largest sizes measured in the series of individual particle images are assigned as the 3D sizes for that particle. The smallest size is assigned as the thickness for that same particle. A few samples were chosen to demonstrate use of the 3D mode on the Partan 3D image analyzer. The coin pictured in the upper left was run as a sample of multiple identical coins to illustrate the 3D results on a set of particles whose three major dimensions were measured very accurately on a set of vernier calipers. Length and width are 14.8 millimeters and thickness is 1.18. We'll also show 3D results of a curved particle sample. The sample in the lower right is a mixture of sand and reflective glass beads. These two components of sand and glass beads have a number of dissimilar morphological parameters, which allow them to be isolated from each other by separating them into their own distributions or classifications and displaying both isolated from each other on a scattergram, which we'll soon discuss. This is the view particle screen following the 3D mode analysis of the sample of identical coins. Two rows of the scrollable image file are seen at the bottom. In the 3D mode, all the images in each row are images of the various random orientations of only one particle as it tumbles through the sensing zone. This means that the chances of capturing images that show very near the largest length, width, area, and perimeter, and the smallest thickness is far better than seeing near all three of these dimensions in only one particle image, which is all one sees in 2D analyses. Here the upper row of images were analyzed in 3D mode. So they represent a series of images of the same particle in random orientations as it's photographed tumbling through the sensing zone. The caliper measured coin thickness, again, is 1.18 millimeters, length and width 14.7 millimeters. The 3D length deviation is 14% larger than actual. The actual width has a 6% larger deviation from measured, and measured thickness 43% larger than actual. The 2D analysis, on the other hand, with every image in the lower row representing different particles, has an actual 2D width value 635% larger than measured, because it gives a width value for every orientation from smallest, the actual thickness, to largest, the diameter. Recall that the smallest width is assigned the 3D thickness value. So when there's only one image per particle, width and thickness would be assigned the same value, which makes the so-called D thickness meaningless. Actual length reported in 2D is 4% larger than measured, so it's very close in both 2D and 3D. This is to be expected because the actual length of the image, or the actual diameter, is projected in all images. Whereas, as pointed out before, the width can vary from the diameter in one image to the thickness of the coin in another, and all distances between those two. This is the XY graph display showing the 3D in green and 2D in red thickness distributions of the measured coins. Note the very large difference in the graphical distributions, with the 3D distribution very narrow with its mode near 1.7 millimeters. And the summary data in the lower right window gives a D50 of 11.6 millimeters for 2D and 1.76 millimeters for the 3D measurement. 1.18 millimeter is the actual thickness. This is another confirmation that thickness can't be measured in 2D. In this slide, you see the measurement results in 3D and 2D of a sample of a common pasta, which has similar sizes particle to particle, but not as precisely similar as the coin sample. And the results shown are the cum percent finer than distribution for, in this case, the length parameter. The three particles shown above measured near 9, 11, and 12 millimeters by calipers to give an example of the lengths of these particles. The red and green cum finer length distributions on the left are the 2D results taken at two different camera frame rates where there's not much difference. And the D50 value for 2D is near 8.4 millimeters, less than any of the three measurements made by calipers. The 3D D50 value in black curve, on the other hand, is near 10.7 millimeters, which is the average of the three caliper measurements. 3D, again, giving a much more accurate measurement. In summary, here are the three major points to remember about the three-mode analysis. Three-mode accumulates multiple randomly oriented images of each particle. The 2D mode collects only one randomly oriented image of each particle. The 3-mode will have images of one particle which show sizes of the three major dimensions, length, width, and thickness, which are much closer to the actual dimensions of the particle than the 2D mode will show. Shapes are calculated as ratios of size parameters on a scale of 0 to 1. So the 3D shapes will also be much more representative of the overall shape of the particle than 2D would give, because the 2D mode doesn't have access to the most accurate sizes. And Microtrac's Partan 3D is the only image analyzer with a patented 3D mode. This is the scatter diagram display, which shows measurement results in yet another format. The red distribution graphs at the top and right side of the blue scatter diagram can be chosen to display any of the morphological parameters in number or volume distributions. The blue scatter diagram shows the location of each particle measured relative to its position on the two red parameter graphs. In this example, length is displayed on the top graph and ellipse ratio, an aspect ratio shape parameter, on the right graph. The scatter diagram can be used to quickly explore the relationship between any two morphological parameters and then to isolate areas to focus on those of particular interest, as illustrated on the next slide. Here we've isolated a small section of the previous scatter diagram by using the cursor to outline an area within the green rectangle on the scatter diagram. Both red graphs have changed to show the location of only those particles within the green rectangle, a so-called classification. This is a quick way to isolate areas of a scatter diagram to note the relationship of two parameters at points in the distributions of special interest. This View Particles displays contains the entire scrollable image file, 2D and 3D data in the upper right-hand corner for any particle selected, and can be used to create higher dimension classifications, not limited to 2, as in the scatter diagram. Clicking the Search Particles button opens the particle query window seen here in the middle of the display. This window can be used to establish any number of classifications containing any number of parameter limits. When a classification is chosen, the image file and the scatter diagram display and list data for only those particles in the classification. The sample shown is a mixture of sand, good glass beads, and bad or misshapen glass beads mentioned briefly earlier. And many other types of classifications and filters can be set up for other types of materials. In this display, we see the top row of images as multiple orientations of one sand particle, for example. In the second, a row of images of one good glass bead, and finally, one row of randomly oriented images of one bad glass bead, which turns out to be several beads fused together. Here a search has been applied and a classification including only particles within the entered length and ellipse ratio intervals, shown highlighted in blue above the search criteria. The images shown here are sorted by descending order of length, and those values are given in each image. We've looked at two ways to investigate classifications within a given analysis result, in the scatter diagram and more extensively in the view particles display. Once pertinent classifications have been discovered using these methods, they can be permanently set up as SOPs or standing operating procedures that automatically create them whenever a sample is run using that SOP. This is the screen in the software in which not only classifications can be defined, but also filters. I won't go into the details of how this screen gets created, but it's well covered in the manual. Instead, I'll explain how classifications and filters are used, and they are exclusive to image analysis, size, and shape technology. Classifications can be used to identify and isolate different components or types of materials within one sample. Classifications are generally inclusive and can be reported as individual sample distributions. Filters are generally exclusive and are used to filter certain types of particles to be excluded from the overall sample results. The classifications defined in this setup screen have been applied to the following slide illustrating the use of classifications for the reflective glass bead sample analysis. This is a scatter diagram of only the good glass bead population within the total sample. It's shown isolated from the total sample mixture. The X graph shows width and the Y graph shows roundness. So we see here a distribution from about 200 to 800 microns in size as width, which for spheres like glass beads closely matches distributions for length, thickness, and equivalent area diameter. The roundness graph shows very spherical particles in this distribution with a mode at about 0.87. 1.0 would be a perfect sphere. We can also isolate, by creating the classifications shown in the previous slide, the sand and the bad beads. Combinations of these classifications can also be displayed. This is the overall sample of a mix of sand and reflective glass beads plotted as cum % finer distribution overlays of the entire sample, the transparent particles, the good beads, the bad beads, and the sand. The transparent particles make up about 70% of the total sample in volume, the good beads 45%, the bad beads 35%, and the sand 20%. And all of this information is obtained from one analysis of the total sample and the creation of the classifications of the different types of particles. And most analyses, again, are performed in less than a minute.
We hope you found the content of our on-demand presentation valuable. If you would like to send samples for complimentary analysis, please send an email to jason.noga@microtrac.com. If you would prefer that Microtrac would come to your facility, we can also arrange an on-site demo with one of our technical specialists. And as always, you can find additional information by visiting microtrac.com.